The next speaker is Dr. T.Jesan, who is both at the Bhabha Atomic Research Center and at IGCAR Kalpakkam. Jason finished his PhD from here some months ago with Professor Shitabra Sinha. He will tell us about his work in networks as they relate to infectious disease problems. Jason.
Yeah, good afternoon. I'm Jason, Bhabha Atomic Research Center, Kalpakkam. So I had wonderful opportunity to work in Institute of Mathematical Science, Chennai. My supervisor was Dr. Shitabra Sinha, and I worked with Dr. Gautam Menon, IMSc. So I share my work with related to infectious disease modeling, especially dynamical patterns of epidemic propagation. So I cover the three areas. So the modeling of infectious disease at IMSc is, I think, big group is here. I cover especially the first one. I start with empirical data analysis, parameter estimation. In this, actually, the estimation of basic reproduction number for H1N1 pandemic, 2009 pandemic at India. And the second one is, which is homogeneous, the assumption of homogeneous mixing populations, so that any individual in the population can randomly can contact with any randomly selected individual. And then specific to the contagion spreading on social content network models, epidemic spread on the SIRS model on modular network. Then the last one, how the role of spatial geography in the spatio-temporal propagation of epidemic patterns. So first one is epidemiological dynamics of the 2009 influenza H1N1 outbreak in India. So this everyone knows. The first identified H1N1 infected person in Mexico in March 2009. First confirmed case in India, May 16, 2009 at Hyderabad, a passenger from abroad, USA. Initially, most of the cases are from the persons who are coming from abroad. But towards the end of the July and starting of the month of August 2009, most of the infectious cases appear to be spread into the resident population because the infection got the momentum and it spread in India. So by 11 April 2010, 30,352 confirmed cases and 1,472 deaths. So this is geographical aspects of the incidence of H1N1 in India. Here you can see, so this is logarithmic scale, y-axis, and different cities. So during this month of end of July and starting of, you can sudden rise in infected cases. And another thing is, so 6 of the 7 largest urban metropolitan account for 70% of positive cases till September 30. So this justifies our assumption because all the urban areas in India are well connected through railway transport, rapid railway transport system as well as air route. So the source of the data is the daily update situation updates from the website of Ministry of Health and Family Welfare, Government of India. We have used up to September 30th positive cases. So we estimated the basic reproduction number. So what is basic reproduction number? It's nothing but the average number of new secondary infection caused by the primary infected in a wholly susceptible population. Because the initial period, there is no interventions, there is no controlling measures. So during that period only, that basic reproduction number is has to be estimated. So R0, it is mentioned R0. If this R0 is greater than 1, the epidemic will spread. So how to calculate R0? This is a general trend of any epidemic. So initially, the number of cases will be stochastically fluctuating, and number of cases also small. So once it's got the moment of the infection, it rises rapidly. The number of cases. So this is x-axis is a time, and this is the number of incident cases. So this exponentially it rises. So this period only we have to calculate the reproduction, basic reproduction number. So once it's the number of susceptible population, number of individuals in the population also, susceptible individuals in the population decreases because of the number of infected cases are more, and the control measures, so it's saturation, it reaches maximum, then it comes down. It may dies out, or it's endemic. Endemic which means number of, still the infection is in the population. That is number of positive cases here and there we can monitor. That is called endemic state. So this way, this exponential growth rate that are not the relation we get exponentially, this lambda is an exponential growth rate. So this we have to calculate the estimate that this tau g is mean generation interval period. This is, which is defined as the time period taken by the secondary infected individuals from the primary infected individual. So this we have taken as a tau g, we have taken in our calculation as 3 days. That is from Mexico. First they estimated the reproduction, same value we have taken. So this is logarithmic of, so how to, slope is very simple. We can, this number, this is the days, and corresponding the logarithmic of the cases, number of cases in the y-axis. So just we have to calculate, take the slope lambda. But the problem is which exponential period we have to take, or how many days we have to take. There is exponential growth period itself, because the data is so fluctuating, and it's very difficult, because if that's why we have estimated the slope for the from June 1st onwards to 8th of 20th of August, all the starting periods, and a different duration window period. The slope we have taken, say from 7 days to almost 38 days something, 40 days we have taken. We have calculated the slope for all the starting days and corresponding to the different window period, and correspondingly the correlation coefficient also we have taken. So here we can see the correlation coefficient, and this is the p-value. P-value which means, say p-value is less than 0.01 means it's the correlation coefficient, or whatever the estimation of the slope is, estimated slope is, the random chance is only 1% due to random chance, if p is less than 0.01. So we estimated. So what our motivation is, the slope and where the correlation coefficient is higher, and same time the p-value should be less. So, and this happens to be here. Here we can see it is during the period from end of the July to starting period up to 8th, I think. That period, the exponential slope, the period of July 28th August to 12th of August 12th. So here we have taken the slope we have estimated. So only for the R is correlation coefficient is greater than 0.7 and less than 1. So this is R cutoff we mentioned, and for all the values of p less than 0.01. So for this average value of lambda, that exponential growth rate lambda, we got 0.15. And the corresponding tau g, that mean generation interval type 3 days, are not equal to 1.45, we estimated. So this is actually we did for 5-day moving average. And moving because the data suddenly it will be 0 because the data is so much fluctuation. Even Saturday, Sundays it may not be there, but it is in reality it will not be there because the website. So we have taken the moving day, but the pattern will be the same. The pattern, what is the time series pattern will be same. And for we have calculated in order to robust estimation, we have calculated for the different from 2-day moving average to 10-day moving average. Here also we can see around this R cutoff value for 3 to 5-day moving average. Here it comes around they merge after R cutoff 0.9 they diverge actually. So here also we have taken this average slope lambda to be 0.15. So this R naught 1.45. So then we the range how much so we have used a bootstrap estimate. It is nothing but the random sampling, but the random sample will be the same size of the original data set. So we can take so many samples and then we estimated. So this is for different periods that average exponential growth rate. And here also we can see, I think, curves of different duration are 31st. So here it intersects. So around 0.15 only. So this is also our bootstrap estimates. Here also we get the same, almost approximately equivalent to 0.15 value we got. And this is one distribution, how the bootstrap estimation distribution for July 31 to August 15th. So distribution of the lambda value. So we calculated, as I told you, we estimated the R naught for the whole India with the assumption of homogeneous mixing. And we also calculated for the different cities and region or city. So Pune, but here we can see the Pune is R naught is 1.74 and Mumbai 1.65, Delhi. And southern region includes the Bangalore, Chennai and Hyderabad. Why we included these 3 regions are well connected through buses as well as train routes. And also the data is, I think almost very much, number of infected cases also slightly less. Not that much, but slightly less. This Hyderabad and comparing to Pune and Mumbai. So that's why we have taken. And so why Pune is higher value? So there are so many whatever our clarification interference. What we can give the ideas or what is the clarification. So one Pune, the climate plays very important role. So the Pune is because its altitude high and it's a very relatively cold climate and the humidity is higher. So the infectious H1N1 can spread more. And another, this is mostly observed. The people at Pune, possible spreading, in fact, testing centers where people flocked at large numbers. That is initially. So that could be one of the, that also could be one of the reasons. So, okay, what is the worth of this estimation of, because reproduction, basic reproduction, because this number seems to be 1.45. Okay, it is, it gives an idea about the government official for policy makers, how much the infection is transmissibility, or how strong, what is the control measures we can make it. This gives our idea for policy makers. So this is one of the, I can give the, so this is February current science is published. So even though India has over 28,000 confirmed cases and 11,152 deaths, no epidemiological analysis of the Indian outbreak is found in the public domain. So we published, I think for April. So this Thailand, I think, yeah, Thailand paper, yeah, they also estimated the same H1N1. So in the WHO Southeast Asia region, India is the only other country to have reported estimates of R naught. So what I want to say is, even in India also, as next time, I think Dr. Professor Sitabra and Gautam, they involved, even government aims, they, whenever any meetings, any urgent meetings, the Department of Health and Ministry of Health and Family Welfare, they want to have the numbers actually. So this is one of the factors. I think they are, even I also involved. So this, what I want stress is, so the analysis of the whatever time series data is very important. It will be useful for the policy makers, for government officials. It will be very useful because they want number. In order to take decision makers, they want to have numbers actually, and they want the support from because it's affect the whole society. It will affect. It may be not only medically affected, it will be economically also it will be affected. If one thing, all the transport system has to be monitored, so many things, implications are huge. So as I mentioned, this is, we estimated, it's a homogeneous mixing population, but in reality it is not like that. So, and another thing is we have to accurately calculate, we need more data. Accurate data. So when the individual who infected who, that spatially that data is required. Just we had only from through the time series data we estimated. So and another thing, time varying estimate of reproduction number. This is basic reproduction number or not. So because due to intervention procedure, how effective the intervention procedures like quarantine, whatever governmental intervention is, so how effective. In order to estimate that, so we need to have a time varying reproductive ratio. That also we have to assess. We need to have the data, more accurate data we require. And independent estimates the generation interval. So I told you that I informed 3 days we have taken mean generation interval time. So we have to have how for Indian climate and Indian population thing, how the mean generation interval time is, we have to estimate. And the final thing is, the important thing is, as I said, the contact structure. So how one person, how the social contact network structure is very, very important. How the epidemic spreads from one person to another person, that is a very important thing. So in this way, we proceed, in order to proceed further, so we have simulated, we have taken the modular contact network where the epidemic spreads. So how does the community or the modular organization of social network affect the epidemic propagation? So especially in this persistence of the epidemic, that the endemic stage we analyzed. So importance of this is spread of SARS from Taiwan 2003. So here you can easily say it's a modular, it's a, that squares are locations, Taiwan, it started Taiwan. So even that CDC director mentioned social contact networks over which epidemic spreads have modular character. So what is modular network? So modular network is individuals in a module or in the community, they have interaction, close interactions, they have intense interactions. Comparing to the other modular network, other module peoples, they have sparsely connected or rarely they social contact or contact with other members. So here the 4 modules. So you can see within the module they have very good connections are there. These are nodes, and outside they sparsely connected. So we used one model parameter R. This is ratio of inter to intermodular connection density. So how many connections with other module members divided by the within the module connection density for fixed average degree of k of the nodes. So here we can say if R equal to 0, so all modules are isolated. There is no connection with this. And similarly R equal to 1, it's a homogeneous random network mixing. So everyone can have interaction with contact with anyone. But if say for R equal to 0.1, so it's in between the 2 extreme cases. So within module they have that individuals in the nodes have strong connections, intense connection, but with other module members they have sparsely connected. Flow means it's a contact. Say if you are, I think you have taken the in a broader structure, I think countries and so, we take small, say within this now is a time variant. Here we have very good connections because we spatially close together. But when the, and of course, another thing is in people who are working in IMSC, they have close connections. So now you are sparsely connected. You travel from here. So you are from other module, say from different place, say Mumbai or Delhi. So this is one module. So you take another module, but you have contact here also. But this is rare. But people in IMSC, they have very good intense connections within among them. So this is one of the empirical data in Karnataka village. I think this, Science is published recently. So here also module. I think this Chandrasekhar in Dr. Sitabra's group is doing this one. So these modules are there. What is in the social contact network? So modules are these different colors implicate the different module members, individuals in the different modules. So I think the 78 villages are there. So this is one example of a 52nd village actually. What I want to stress is modules are very important in the social network. This is a reality. Someone may not be the ideal, but it's closer to the ideal. So in this modular network, we investigated the transmission of epidemics in modular continent, in particular persistence. So what is persistence is always the number of infected persons are always greater than 0. So here 1 and 2 or any, it could greater than 0. So for longer time periods, so t tends to infinity. So here this is the endemic state. So this is a persistence. If persistence, the epidemic is persistent means here the number of infected cases are still in the populations. So for simulation, we have used the SIRS dynamics. SIRS model is susceptible to infected and infected to recovered. So susceptible person is infected by the probability alpha, and the infected person goes to recovered state after period of tau I, say 5 or 10 days like that. Then he recovered persons may have the immunity, temporary immunity. He may lose the immunity after fixed period of tau R. So he again go to the susceptible compartment. So this simulation, so we have taken the network size of 1024, and this number of modules are 64, module size is 16, average degree 12, this is realization of 100 realization. Here we can see interesting results. So we have simulated for this axis R0, and this is a modular parameter R. Here we can see for lower R0, it's greater than 0. So it is less than 0, less than 1 R0, it cannot propagate. So the number of infected persons in a longer period, it may not be there. Only few days it will die out. And similarly but for this is homogeneous random network, R equal to 1. And this is almost 10 to the power minus 4 means it's almost isolated modules. Here we can see in between the R equal to 0.002, the epidemic is persistence. We can see the number of period almost is 10,000 days we simulated. Still it is it is not still the number of infected cases are there. But for R equal to 0.02, it rapidly extends. Higher or the higher means modularity is less. So the homogeneous, it tends to homogeneous network, it's dies out. Similarly, if it is almost isolated modules, this R is very less, then also it is dies out. So what is its, but for a critical range of modularity for contact network, say R0 approximately, here you can see R equal to approximately 10 to the power minus 3, highly infectious contagious are persistent. Only for highly infectious rate. For a lower infectious rate, it's not persistent. Say this peak only. This shows highly infectious rate. Say for this is for R naught around this white dotted line is for R naught equal to 6. So why this community structure or the modular network exhibits persistence? So mechanisms, in order to understand, we have analyzed the Laplacian spectrum of the contact network, modular contact network. So this is, lambda 2 is a eigenvalue, second eigenvalue, which is greater than 0 only if the network is connected. So this is a global time period. So in modular network, two time scales are involved. Within module, the epidemic spread fast, but between modules, the epidemic spread slowly. So the two time scales are involved. So this is lambda 2, 1 by lambda 2, which is the time scale of this global time scale, that is whole through all the modules. So here it decreases with R. And similarly, this is the 1 by lambda of mth. This is a spectral gap, they say, between, say, if the number of modules is 64 plus 65, the gap between the difference between the inverse of eigenvalues of number of modules and plus 1. This gives the spectral gap. This also decreases. But for the ratio between them, here we can see it's monotomically dependence on, so non-monatomic dependence on modularity. There is not that much. So what we found is the infection spreads fast within the module, and same time it repeats to the other module. It slowly spreads to the other modules. Same time it comes to the again to the thing. The infected persons recovered persons become again susceptible. So that's why its persistence is going on. So in the modular network, so this is optimization of the between two time scales. So the contagion spreads slowly from module to module, allowing the parts of the network to recover before return of the infection. Again the infection return, it's ready to infected. The recovered persons lost the immunity, so they are become again susceptible. So this. So modular network, we then go to the what is the spatial role of spatial geography in the epidemic propagations. This we have you analyze the Malbazar block of Jalpaiguri district of. We have data from malaria data, both Vivax and falciparum. 51 health centers we have. So this data is from monthly data, January 2005 to 50 months, February 2009. The number of malaria cases, Plasmodium falciparum and Plasmodium vivax from 51 health centers. So this is the local place, and this place. Okay, this is the block in the northern West Bengal. This is almost the spread is what we here the population according to the population. So this place is where the administrative offices are there, and this place where the forest jungle region is there relatively. The population is less here. This so these boundaries of the 51 health centers are indicated, and their identities are represented numbers 1 to 51. So the time series data of both malaria, Plasmodium vivax and falciparum, they are subjected to the wavelet analysis. So here we can see, in order to find out the periodicities, how they are repeating. So the wavelet analysis, we can get the period is dominant period. Is a dominant period. Every year it is coming. So 1 year almost we can see the maximum, the peaking is. And similarly for falciparum also it is increasing. So next we use the wavelet analysis to find out the epicenters. So which place the malaria starts and spreads to other places, how it propagates from one place to another place, which is the epicenters. So for this we have, in wavelet analysis, each time step, the one phase angle will be there for each health center. The time series subjected to wavelet analysis, one phase angle. And then mean relative phase angle is we calculated, and for corresponding to one period cycle. So we have taken the 12-month scale, that is 1 year we have, because it is repeating every 12 months. And this mean relative phase angle is obtained from the average of all the spatial average from each health center. Phase angle is subtracted from spatial average for all the health centers. That is a mean relative phase angle, MRPA. Then which is the highest phase angle? That is the epicenter of the epidemic. So here we can see for mean relative phase angle for Plasmodium vivax, it is 43. This place is the highest phase angle, this is epicenter. So, and for here, two places it comes. This is expected, it's administrative location where the people can go from all the places to, they can, administrative offices are there. And this is also located near to this forest area. And what we found is here in this place, so many irrigation projects are going on. So during this period, that 2006 to 9. So usually this epicenters are expected. Say, I think yesterday also measles, they said London from urban areas to only travel to peripheral places. But here, where the population is highest, or population density is higher, from that place to it will spread. But here it is in between, especially for this work. So we have to analyze what could be the environmental factors responsible for this epicenters, because these results will be useful in order to pockets of location we can identify. What is the benefit of epicenter? We can identify in order to intensify our say vector eradication, malaria, the mosquitoes eradication programs can be intensified in that locations, because these locations are the epicenters from where the malaria spreads, starting point. So this is how it travels from this is so distance from the epicenter to other places. So how this is linearly it's correlated. So as I mentioned, it's as we expecting, what could be the reason? What are the periodic forcing? Because every year it is dominant periodicity we found 12 months. So one of the rainfall, for malaria, mosquito breeding will be the rainfall. So we use the rainfall, but we use the rainfall for the whole district data only we got it. So here we can see, so this is time series data of rainfall and malaria cases. So they are almost with some delay, because after rain the mosquito breeding may take place. So after the adult mosquito may come out. So in order to find out, we have delay in months, delay in months and the correlation coefficient between incident and the rainfall. So we have found for Plasmodium vivax it's 1 to 2 months. For Plasmodium falciparum, we found 2 to 3 months. So this could be useful when to we have to intensify this time delay, when to intensify our malaria eradication, vector eradication programs we can intensify. So these results could be useful. So in order to why the periodicity, how it periodicity is come. So for that I have used the model, detailed model. So 51 health centers has taken 51 nodes, and they are connected through depends on their distance from their location. From say one health center is how much distance. So for example, the urgency, it depends on the urgency matrix. So this is based on the McKinsey model, how the malaria spreads, but with the network model, spatial network model. And this urgency matrix, which is defined as what is that? If a threshold value, say DC, if it is greater than this value, it will be 0. If it is less than that distance, say 6.5 kilometer, it will be between the two health centers, I and J, it will be 1. They are connected. So through this network model, so I think all the parameters are, this is proportion of humans in node. So each we have population density also. No? So each node, how many, this Xi is a proportion of humans in node I who are infected. So all data we included. So this is a result. So this is here we have this is adult emergence of adult mosquitoes with constant thing, this blue color dotted line. Then the fraction of infected humans is through simulation. It's not periodically. It's non-periodic. It's just monotonically there. If in all the health centers, but once it is varying adult mosquitoes varying with 12 months period. So again we all the health centers we found the periodic with 1 year period. So we conclude that there's one of the factors, rainfall could be the one of the, could be other, in order to model other factors also available, is like temperature and humidity, so many factors. The rainfall is one of the factor. So these results, as I mentioned, what is that, periodicity, when we have to intensify our mosquito eradication or vector-borne disease to control vector-borne disease, these results will be useful. So actually, I once again thank honestly I'm telling after my PhD thesis defense, I deeply involved in my work at Department of Atomic Energy, so fully radiation. After a long period, and suddenly they gave me, I think here it's a wonderful opportunity. So here working in IMSA, I should will be very happy always. So I once again thank Dr. Sitaprasan and Dr. Gautam Menon for giving me the wonderful opportunity. Thank you very much, sir.
We have lots of time. Questions?
Yeah. If you have R0 is nothing but actually number of secondary infected cases, average number of. So if you have accurate data of initial period itself, say if you have whoever the contact structure, this person infected this person from there he got it. Say from one person is coming from abroad. How his contact, who are the possible person he contact, how he got it. Other persons, secondary infected, how he got it. That chain structure is if known. So his R0 is like that. So it's if one person, so he can infect so many 3 or 4 persons. If it is R0 means if secondary infects are 3 from one person, it is R0 is equal to 3, like that. So if you have detailed data in initial condition itself, you can immediately. I think Mexico and these places they have estimated. Even Mexico, because they know immediately they come to know this person. What I want to say is follow up of the infected person or the history of the infected person. Then immediately this at least even 10% if you know accurately, immediately initial condition itself we can average only. It's average. So how effective this infection is, we can estimate initially itself. So one thing is detailed, the population is less, and we know the good administrative controls are there. Data collection is very important, so in this case. Sorry, sir?
It's mainly based on the incidence and the incubation period. Those parameters decides the incidence of spreading the disease.
Yeah, that also
So
mean generation to team.
Actually,
Yeah.
so incident means either you can calculate per hour basis or day basis or week basis. Based on that, you can able to calculate R value.
Yeah. If you want accurately, even hourly, but days, okay, I think everywhere. Days.
So it's all mainly depends on the incubation period.
Yeah,
So it may be varying. From
Yeah.
days to
This is for average. Even some people they used 4 days, 5 days. But Japan they used, but they clarified
So
why they
always
used
you
because
have to take into consideration average incubation period. So average incubation we have to take into consideration. Then you have to see the number of incidents. So based on that you have to calculate.
incubation period actually the mean generation interval is slightly different from incubation period, but people some people defined incubation period plus the expression what is that after the infection is there so many slightly different definitions are involved. So there are so many techniques are there. For all of this, I think for a real epidemic thing, we have to have data. That is if that then it's everything.
Pakka monitoring and as well as surveillance system, MOS strategy.
Yes.
You can able to calculate the R value as modeling.
Yes.
So Pakka MOS system is required in view of developing model.
Yeah. The data is. In H1N1. For this is a simulation only. This I think is second. The modular network you are asking, no? Here. Number of time series data. So this time series data we have. So I think for all the cities in India we have. From time series data only we just estimated R0. So based on this, say R0, this I told So initially the values are very much fluctuating. Here we can in newspaper we can say 1% they found H1N1 and there, but when it's epidemic, it means it got momentum. More people are infected, then it rises exponentially. This period only. For this method, whatever observed data we have, this method is the ideal thing. So if we have detailed data, this method may be not required. Initially, it's what Abbas asked. Like that, immediately also we can calculate this whatever existing data we have. So this is a general trend. So it rises exponentially once it got momentum. So initially we hear person, there are person fluctuating. One suddenly 10% infected, and another day no results like that. So it is circulating some here and there. Then once it is somewhat in the environment, it is fixed. Then it's if no control measures are not there, it suddenly rises. That is why exponential phase. So we calculated based on that slope only. So this reproduction number we estimate.
Sir, here. Sir, come to that malaria model.
Which part?
Last one, sir. That model, differential equations.
Okay.
Okay, sir. Sir, here you have not considered that mosquito population, sir. You have considered.
Yeah, mosquito population. MI.
MI. Okay.
Capital MI.
So that is epsilon T.
That is emergence rate.
Yeah. Okay.
Adult mosquito. This only time varying. So the two results I have put this is only constant thing.
Okay.
This is a time varying thing. Then because rainfall and emergence rate of mosquitoes are related, so after only it will, I think whenever the eggs are touched by water, then it will come out. That larva will then after 15 days to 1 month, adult mosquitoes will come out.
Okay, so the interaction between human and mosquito, you have not much considered.
No, it is there. I think it should be there. Something, it's there. here.
Here, ACXI, last one.
Yeah.
Okay.
Yeah, it is there. It is there.
Okay.
Interaction. I think this is very standard model. I think the Smith deal. No, they.
Okay.
So I have used in network. That's all.
Okay,
Network model, the diffusion coefficient, everything, and how urgency. So another thing I want to mention is I told you this urgency matrix. So where the connection between I and J is 1 or 0 depends on, I said, 6.5 kilometer. It is not distance sensitive. Even if are taken for 10 kilometer, it's not that much. Results are not varying. The periodicity is coming. It's not sensitive to that distance or threshold value. This urgency matrix.
Okay, thank you, sir.
Any more questions? If not, let's thank Jason for his nice talk.
Thank you, sir.
Just a couple of reminders. If you would like to give a talk but your name is not on that list, please come and contact me. Write your name on a piece of paper with the talk title that you'd like to give. Talks will be typically about half an hour, 20 minutes to half an hour. They'll be slotted most likely on Friday or Saturday, I think. And there'll be enough time for you to prepare if you need time to. Then we have a lab session at 2 o'clock in the afternoon. So come back by about 1:55, 2 o'clock to the lab room upstairs. Okay? All right. Thank you.